In this video, we're going to take a look at two examples of being able to take the inverse Laplace transform when we start having that unit step function involved. So we want to find the inverse Laplace of e to the minus 2s divided by s cubed. And one of the things to note right away is that because you have this e to the minus 2s in the numerator, right away that's going to be a unit step function. So you're going to have the unit of t minus a. And in this case, we have that a is going to be equal to 2. Right? Now, the other thing we have to do is we have to kind of think of this as L minus 1. And we're going to pull that trick where we multiply the top and the bottom by 2 over 2, because we need to set up the numerator to have the same form of Sn plus 1, and the numerator we have n factorial. We're also going to have the e to the minus s, 2s, excuse me. And that might help you to see what we're going to do with this. Now I'm going to factor out a 1/2. And we have L minus 1, 2 over s cubed, and then we have the e to the minus 2s. And now what we're going to do is we're going to remember that this is going to say that we're just going to take the unit step function as well as the function itself and insert t minus a. So now we know that the Laplace inverse of just this part right here, that's usually going to be just t squared, okay, if we were going backwards for that. But what we're going to do is we're also going to consider this e to the minus 2s where a is equal to 2. So when we finally find the inverse of this, we're going to drop down the 1/2. Instead of t squared, it's going to be t minus 2 squared. And then we're going to have the unit step function t minus 2. And this is your inverse Laplace transform. Okay. Now, a little bit tougher example is this animal right here, where we have e to the minus 2s divided by s cubed minus s squared. So this is a familiar type to where we might have to do the partial fraction decomposition, and not just might, but we will have to do that. So let's start with that, and let's just ignore the e to the minus 2s for right now. And let's just kind of decompose the 1 over s cubed minus s squared, or we could think of that as 1 over s squared s minus 1. And when we decompose that, that's going to be 1 over s squared times s minus 1 is going to be equal to a over s plus b over s squared plus c over s minus 1. We have a repeated linear factor right here. Another way to do this, by the way, this isn't the only way to do it. Another way we could do this, and I'm going to erase this in a moment, is that 1 over s squared plus, or times s minus 1 is going to be equal to as plus b over s squared plus c over s minus 1. That's another way to do it, right? However, I'm just going to stick with this way of doing it for right now. And so to clear out our partial fractions, we're just going to multiply by the common denominator of s squared s minus 1, and then s squared s minus 1, s squared, and then s minus 1, and then finally s squared s minus 1. And here's what we're going to be left with. On the right-hand side, or the left-hand side, excuse me, we're going to have 1, and then we're going to have as plus b, excuse me, as times s minus 1, plus b s minus 1 plus c s squared. And don't forget that we over here, we're going to have 0s squared plus 0s plus 1. And that's just so that way we can go ahead and set up our system. Right? We can go ahead and rewrite this as as squared minus as plus bs minus b plus cs squared. And now we can set up our system really nicely. So again, thinking that we have 0s squared and 0s, our system for this is going to be that a plus c is going to be equal to 0. All right, so the s square and the s square is going to be equal to the s square. Then we have a negative a and a positive b is also going to be equal to 0. And then finally, we have negative b is equal to 1. And now we can see this is a really easy system to solve because right here we see that b is going to be equal to negative 1. Right here, we can see that a is also going to be equal to negative 1, since the opposite of negative 1 plus negative 1 is going to be negative 1. And then right here, we can see that c is going to be equal to positive 1. So now we can go through and finish this off because now we have the decompositions. And we're going to remember this e to the minus 2s that we had at the beginning. All right, so the decomposition for this, and let's be really careful about this when we write it, that's going to be L minus 1. Now remember we had a and b were both negative 1, so we have negative 1 over s, negative 1 over s squared. So we have negative 1, and remember we have the negative or e to the minus 2s over s plus negative 1 e to the minus 2s over s squared. And then finally we had c, which is 1 e to the minus 2s over s minus 1. All right. Now, what would probably be helpful for us is to split this up into 3 different inverse Laplaces. All right, so I'm going to do so. So we're going to have L minus 1, and I'll just pull the negative out from right here. So we're going to have e to the minus 2s over s, another negative, inverse Laplace of e to the minus 2s over s squared, and then finally, we're going to have plus inverse Laplace, and hopefully we don't run out of room, e to the minus 2s over s minus 1. Great. And so finally, when we do this, what we can do is we can just kind of pull off these e to the minus 2s's. So I'm going to do these one at a time. So we have negative inverse Laplace of e to the minus 2s over s. All right, so that's going to work out to be the opposite. So we have 1 over s. All right, so let's just think of this as inverse Laplace, and there's still a negative there, of 1 over s e to the minus 2s. All right, and we can see that a is equal to 2. And so that's going to work into, we know that this is 1, right? And there's nothing to plug into that, so that's really nice. We still have the negative, and then we're going to have the unit step function of t minus 2. All right, so let's hold on to that. That's one part of our answer. Right. Now, for the second part of the answer, now we're going to have a t in this part. All right, so this part up here. So we have our negative inverse Laplace, and I'm just going to break the e off right away. It's 1 over s squared, and then e to the minus 2s. Right? Now, we know that e or 1 over s squared is just going to be t. Right? So we know that the inverse Laplace of that is going to be t. But we know that a is going to be equal to 2 from our second translation theorem. Right? So remember, the second translation theorem says that, okay, well, now I have to replace t with t minus 2. So we're going to get the opposite of the quantity of t minus 2 times the unit step function of t minus 2. So that's going to be our second. And then finally, what we can do is we can just go ahead and do the third. Right? So the third one's a little bit sneakier because it's actually going to use both the first and the second translation theorem. Right? So now this one is a positive, so we're going to have inverse Laplace of, I'm just going to say 1 over s minus 1 e to the minus 2s. All right. And what we could do is we could actually rewrite that as s approaches s minus 1. Okay, so let's just go ahead and rewrite this as 1 over s as s approaches s minus 1. All right, and that can help us out a little bit to be able to work with that last part of the 1 minus s. And so we can rewrite this down. We know that the inverse Laplace of 1 over s is just 1, so that's easy enough. We don't have to worry about that. And we know that with our e, all right, that's just going to be an e to the t right here. All right, so remember that's going to be an e to the 1t. So one way that we might be able to write this is we can say, but instead of t, we're going to have e to the t minus 2. All right, because we're going to replace 1t with t minus 2. So this is the first translation theorem, and this is the second translation theorem being used in tandem. All right, so when we finish this off, this one is going to become e to the t minus 2 times the unit step function of t minus 2. All right, and now we can finally write the entire answer. Right? One way that we could write this is we have our first, which is the opposite of u t minus 2. And then we have minus the quantity of t minus 2, u t minus 2. And then finally we have plus the e to the t minus 2 unit t minus 2. All right, so that's one way to write it. Another way to write it is noticing that we have negative 1 of these, and then we have negative t minus 2 of these guys. All right, so we actually have like terms. So we could just kind of combine those together. And if we combine those together, we could certainly try to manipulate that a little bit. So if we want to distribute it, this would be a positive 2 and then minus 1. So we would end up with the opposite of t minus 1 and then unit t minus 2 and then plus e to the t minus 2 of unit t minus 2. All right. If we wanted to distribute it, we could get just a positive 1 unit t minus 2. We could factor out a unit t minus 2. So that's probably the cleanest answer we can get. So just to shape this up just a little bit more, a really nice answer we could get is unit t minus 2 times the quantity of e to the t minus 2 minus the quantity of t minus 1. Or if we just want to distribute that to make it even nicer, we could just say 1 minus t in here. All right, so, and that's probably the nicest looking of the inverses that we can get, even though it's not all that nice. All right, so why are we doing all this stuff with the unit step function? Because, well, we're not really doing anything with differential equations yet. Okay, all we're doing is just finding Laplace and inverse Laplace and graphing. Well, what we're going to be looking at in the next video is how do we start solving differential equations that have these unit step functions in them. In other words, if we have some sort of piecewise step function going on here.